National Ignition Facility Program in the Photon Science Directorate. So he joined Livermore originally in 1980, and then from 1990 to 95 was a founding partner of Advanced Technology Associates, and then came back to laboratory as assistant director for program development, physics, and space technology. He got his degrees at Cornell, and he's won several awards for his work, including one for excellence for significant contribution to stockpile stewardship, and that's connected with the National Ignition Facility. So, as most of you know, what we're hearing about today is the world's largest laser facility, and everything about it is on a mind-bogglingly grand scale. And that's what we're hearing about. 192 laser beams delivering megajoules of energy to a millimeter target in nanosecond pulses. That's astonishing, and what we'll find out is how to do that. Now, I was director of a national laboratory for a while, and we ran the biggest accelerators in the world. There we had counter-rotating beams of protons and antiprotons. They each carried about a megajoule of energy each. I did see what happened when there was not a completely controlled loss of these, and it's very impressive. And so a lot of what Ed's been worrying about is how to make sure these beams go where they're supposed to go, and in a controlled way. We had protons, they lose their energy in a very different way. But I know you've been reading about the Large Hadron Collider at CERN, where they have proton beams there, 300 megajoules of total energy in each beam when they'll be put on it, which is roughly the kinetic energy of the Saget Bay, the bullet train. So we're in a new regime of how to deal with things. But this is the world's most powerful laser, and it's something that has been the dream of this community for decades. So today Ed will talk about laser fusion energy, opportunities, and challenges.
Yeah, I have a couple of things to say. You know, I have 3 daughters who are 19, or I think 19, 20, 24, 20, 25, and 30, and you know, they all got into UC Santa Barbara, and I said to them, you know, if you come down here, I will come down here with you and take your courses, because this is such a beautiful place. Alas, they didn't, but but I'm glad to be here myself, and I want to thank you for the kind introduction, and I'm going to talk to you about you know, something that's really interesting, laser fusion energy, you know, and since I've heard that you come from a lot of communities, I'm going to probably be passing back and forth between stuff you're expert at individually and maybe not, and try to put it all together in a story about what is fusion energy, what is laser inertial confinement fusion energy, and what we're doing at Lawrence Livermore to make this all possible. So I appreciate you coming on the last week of the semester. It's really, I know it's not necessarily the easiest thing to do, but we'll see if it make it worthwhile. You know, I know you're all thinking about this. You know, clean energy, I think many of us believe, is humankind's real challenge, right? You know, if you think about the future, where we're going, this is a very interesting map. You know, thousands of cloudless night pictures around the world. And it shows where 6 billion of us sort of live, but it doesn't say a lot about how our energy intensity is. You know, United States, if it were one, sort of on average, the rest of the world is running around 15% of us. And also, there's another 3 billion of us joining up, right? And they're joining up in places that are using low energy intensity right now, and they want to go up to energy intensities probably like Europe, you know, which is about half the energy intensity of us. And because of that, a lot of things are in rapid flux right now. And this is a picture that's notional in some sense, but I think it's instructive. If you look at where we are, which I find incredible about this picture, is that, you know, what was going on from 0 to 1950, right? Just sort of hanging out, right? And then we started going up. You see inflection points sort of in fairly recently, to first order when you guys were being born, right? And now we're sort of moving. And if you look at what people are projecting, and who knows what 2100 really is, but if you look to 2050, you know, we're going from, you know, a factor of 2, 3 times more energy. And right now, most of the energy we use is fossil fuels, as you all know. And what, you know, all the treaties and all the projections and all this other stuff is that we got to get down by 2050 to where we were in the 80s. Now, as scientists, or engineers, or whatever you are, when you see this many derivatives, this many orders of derivatives, you should be suspicious. It's really hard to do that kind of stuff. And what are we going to fill us in anyway? This is carbon capture and sequestration, keep using fossil fuels or biomass, nuclear fusion, renewables. There's a whole bunch of things that we have to figure out what to do with, but it's going to be a hard problem. And let me tell you how hard it's going to be. You can look at history and sort of get an idea. This is the United States from 1850 to today. And, we were a 90% wood society in the 1850s. And over 50 years, we became a wood and coal society, and then became an oil. We added oil, then we added gas, then we had a Great Depression, so we started building dams, right? So we, got hydro. Then we had the second generation of the Manhattan Project, which was nuclear, right? And then we added renewables, right? And this is all energy, right? So this includes transportation, right? So that's where we are. So what's amazing to me is the United States in 1890 was a 93 or 4% carbon economy, and over the next 120 years, we went to an 88 or 90% carbon economy. So we're really deep into carbon, right? And that's because it's cheap and it's plentiful, right? And that sort of drives how societies react. That's what you can get, that's what you can use. Chemical bonds are nice. They store lots of energy, but they have a lot of carbon, which we're becoming to appreciate might not be the best thing for us in the long run. I also want to point out a couple of, the wrong thing. Let me just go back. I want to point out a couple of other things. Sort of takes like 50 years to change technologies. And do you know why? Anyone got a guess? It's always money, right? You invested that in infrastructure. That infrastructure probably will last 50 years. You're not just going to go and throw it out. So even if you have a great idea, it takes a while to make it happen, right? So that's what's going on here. And also what's amazing to me, if you look at sort of in the 70s, things sort of locked in. So, 40 years ago, life sort of locked in. And it sort of stayed this way from now on. So we're in the United States just sort of doing slow replacement of what we have. It's an interesting thing. Right now, people think the infrastructure we have is good for 70 years or so. So if you think about 1980 to plus 70, sort of 2050 is an interesting time. So right now, how old are you in general? 20-ish, right? So 40 years from now, you're going to look like me, maybe slightly better. But so everything that you have today that's here has to be replaced. What is it going to be replaced with is the question. And that brings me to my next point. The basic issues of change that we face. And by the way, this is a talk on fusion, right? Is the fossil era ending? So let's talk about that. If we go back to this, it's hard to believe, right? And if you go to China or Japan, China or India, right now they're building coal at a phenomenal rate. And I think, it's hard to know the exact numbers because they sort of vary, but every 5 to 7 days, China is putting a gigawatt of carbon in coal, the first order. Now, people hear about China is going to be the most green technology system in the world, and maybe might have the most green technology. But the fact of the matter is, I've been in China recently, and they're trying to get in 2050 where we are today. That's their real goals. And that's real hard. That's a lot of nuclear, percentage-wise. That's a huge amount of nuclear, huge amount of everything that they have to deal with. But that is a carbon society, India too. So what are we going to do about that? And what about fossil fuel? What about renewable? What's the availability of that? Say we went up 10 times more than we had now, not counting hydro. You'd get to a few, 10% maybe. That's kind of hard. 20 times, 20%. Doing a factor of 20 on anything is very difficult, right? And is fission experiencing a renaissance? You hear that from the Obama administration and the like. we're re-entering the fission era. I support nuclear fission very strongly. It's really a shame that we're not, in my opinion, that we lost our mojo somewhere around 3 Mile Island, and maybe we deserve to because of the way it was being managed. But it's a good technology now. It's not being used. But if we wanted to maintain ourselves at the 18 to 20% we are now, we have to build like 150 to 200 gigawatt machines in the next 40 years. Right now we have 110. We have to replace all of them and maybe put 50 or 60 more in order to maintain our percentage. So that is also really challenging. And then finally, fusion, the love of my life, is not even viewed as a part of this equation. It's just an R&D program, long-term R&D program. So when I say all that, why I've dragged you out of your last week of celebration. I think you're done with finals, right? No? Even better. To talk about fusion and why is there fusion in your future and ours also. And I think the answer is because fusion is so cool, right? And I think if you look at this picture, this is the amount of coal, oil, fission, and fusion fuel you would need for a gigawatt year. So think about San Francisco, right? San Francisco or any million-person city in the United States uses about a gigawatt of electricity. So if you're thinking about Washington, Boston, cities like that, this is what you're talking about. And you would need about 20,000 railroad cars of coal. And by the way, the amount of CO2 and junk you get is more than that, when you add that oxygen to it. You got super tankers of oil. Well, we'll never make electricity from oil. It's just too damn expensive. We have fission, and then we have fusion. And what's amazing about fusion, 0.6 tons of heavy water is 600 liters, 150 gallons. So if you had 150 gallons of water, heavy water, which came to us in 1 minute after the Big Bang, that's when all of that deuterium and hydrogen appeared in the universe, we would have enough energy in that, if we could burn it as nuclear energy, fusion nuclear energy, to supply San Francisco for a year. Kind of an interesting idea. In fact, all of California needs a small swimming pool of fuel. So that's the good idea. It's non-geopolitical, it's non-polluting, it's non-proliferant, if you could make it work. So the question is there a way to turn this picture into a fusion picture? I gotta tell you, it's not easy, but if you look to the skies above, and this is the Hubble Deep Field picture, there it is. There is the answer. When you look up at the sky during the day and look at the sun, and when you look at the sky at night and look at the stars, that is fusion energy. That is hydrogen burning to first order. And the question is, could we make that happen on our Earth, right? And what's the scale of that and what are the requirements? And the answer is, every time I look at the sun now, I just wonder, is that the source of fusion energy that we control versus fusion energy that we're harvesting now, right? Remember, all that carbon that we're harvesting is because of the photons that have come to Earth as a byproduct of fusion energy in the center of the sun, right? This is where it all came from, and this is where we're going. So could we build a miniature sun on Earth, get that energy directly, and provide significant energy for humankind forever? And the answer, the forever part is really important. Remember, the deuterium, which is the isotope that we need to start this process, and the tritium. There isn't any tritium, but there's a lot of deuterium in all water. You turn on the faucet, you go to the ocean out here, or the bay, one out of every 7,000 molecules is a deuterium molecule, right? And the energy density of that is nuclear fuel is incredibly high. So we think we're getting close to proving the possibility. And we're doing this at the National Ignition Facility, which is just up outside of San Francisco. In the next year or two, we should find out whether we can do this or not. And our confidence in this is growing, over a long period of time. And this is what the NIF looks like, as we call it. And it's one building. It's 5 hectares. You know, I just came back from Europe. Does anyone know what a hectare is? What is it? Right, so it's around 2.2 acres, right? You know, so it's the metric acre, and it's pretty small. So, you know, it's the biggest laser, as you heard, but compared to Walmart or Costco, it's a regular-sized building. You know, I always say, if you went to IKEA, it would be lost somewhere in the living room section, right? And it is kind of an interesting thing. Now, we just talked about protons, right? You know, protons are interesting, but they unfortunately have mass. You know, we do with photons. Photons are remarkable. They carry energy, they carry momentum, they have no charge, they have no mass. We use that to our benefit. So we'll talk about how. The NIF is operational. You know, it's conducting experiments and acquiring great data. And I say great data, I mean the following. It's a flamethrower that no one else has, and it's a precision physics machine that no one, to first order, expected. So we'll be able to get data to explore a variety of phenomenology right now. So I want to talk about the long-sought goal of achieving fusion ignition. So I showed you this big building, right? You know, this 5-hectare building. This is a fusion target right here. And I want to pass it around so you can all look at it. This is full size. By the way, it's solid gold, so I want it back. It's cut in half. Now keep that in mind, right? So that's, you know, that's the size of a Tylenol capsule, right? And, you know, it's 1 centimeter long. And inside, the deuterium and tritium, which are, you know, what like to burn together nice, the hydrogen isotopes that like to burn, are, you know, about 2 millimeters, or peppercorn or buckshot, or a lot of people have different attributes for it. And that's where we do it. In fact, the amount of tritium in that thing is about 1/10 the amount that's in that exit sign. So it's kind of an interesting situation. And we think that this could be the story of our energy future. We're not sure about this, and we'll talk about what it takes to get there. But I want to go back, because this is very interesting. World's biggest laser, but it's a 50-year story. And I say this because when I talk to students and I talk about 2050, and they say, geez, who cares? You know, I think about what people were thinking about in 1960 and how it changed my whole life in view of what I'm doing right now, you know, when I was, you know, at that point, 10 years old. And that was when Charlie Towns, who's a Cal, you know, first put, and he's still alive, 95, still working in the field, put together the idea of what a laser, how a laser would work. He did a lot of work in masers during World War II when the radar was being developed, and then he came up with the idea of the laser. And then Ted Mayman, you know, in 1960, on May 16th, 1960, at 3 in the afternoon, you know, which was 50 years and 2 weeks ago, right, demonstrated the laser with this most elegant device, you know, which is, you know, a man who understood the basic of physics, the basic of technology, and engineering all at once. And that's why Charlie, who's a brilliant man, you know, didn't know how to make the laser. He could think about it, but here's the guy who put all that together. You know, now, the world today that we live in is much more multidisciplinary. In fact, this group of people, the fact that it's an integrated energy group, I think sort of accepts that as a going-in position. And, you know, he just did it all himself. You know, I was up in Vancouver to visit his widow and others and his friends. And I didn't bring the picture, but I got to hold the laser, right? That was a lot of fun. But anyway, they demonstrated that laser at Hughes Aircraft, which I later worked at. And, you know, and knew a lot of people who were around him, including his technician, who I still know, who actually, you know, made the first laser. But what happened was very interesting. Here is Lawrence Livermore National Laboratory outside the Bay Area, 1960, day 3 after the laser, after coherent light. And it looks kind of different than it did today, but at that point, John Knuckles, who later became the director of the lab, understood immediately, to first order, that you could use photon light, coherent light, to make fusion. And this was very classified work at the time. And it remained classified for a long time, for 12 years, until 1972, when finally other people, the Brits and Japanese, finally started talking about it. And so, we fortunately had to declassify the work, and there's a famous paper in 1972 that discusses this idea. But he proposed the laser for fusion energy. And again, we're going to go on a long journey that gets us to where we are today. This is what he said. Why don't you take this oven, build an oven, right? That's the one that's passing around. It's a gold can, right? And why don't you just put a little capsule wall around frozen DT, isotopes of hydrogen, and why don't we just put a little laser light in? He didn't have the numbers right. And watch the billionths of a second go on and heat up this oven to a few million degrees, 300 electron volts if you're a physicist. And why don't we get those X-rays that are coming in the oven to be absorbed by the wall of that rocket and drive it in at high speeds to overcome the repulsive forces of the protons and make it fuse. And so when that happened, and I'll show you this again because I know you're not perfectly expert in that, at the right temperatures and pressures, right, and densities, you can get the nuclear, wave functions to overlap in a way, if you're a physicist, that you will form helium, and then helium-5, and then it'll pop out a neutron and some X-rays, and an alpha particle, you'll get helium out. And if you weighed all that stuff, before and after, you would find out it weighed less than when you started. And where did that mass go? Energy equals mc squared, right? So let's just watch this again. This is what happens, right? Remember that? I hope that target's coming back to me. Okay, so we have the gold can. Gold is good because it has a high opacity for X-rays. It keeps X-rays in, right? We have that capsule wall, plastic, which is good rocket fuel. And then we have the burning fuel, the solid DT. And here we go. Billionths of a second, laser light coming in, heating up really fast. You go from, actually nearly absolute zero to 3 million degrees in the first few billionths of a second, and then you go up to nearly 1 billion degrees as it burns. Now the scale of that burning target is about 50 microns across. So your hair is, is any redheads here? Right, if you're a redhead, your hair is about 50 microns in diameter. If you're a brunette, it's probably 100 microns in diameter, right? So that's the scale when we talk about a miniature sun. Okay, so then we had this guy, just to go over history, because this is important to me. I met John Emmett. He thought of how to, well, I wouldn't say he thought of it, but he developed the approach, the integrated approach to start building big lasers. And this is what Janus looked like in 1975, right? So this is the long journey that we're on. And so then in Argus in 1976, and you can see this architecture is starting to develop, right? And watch what happens. And Shiva in 1977. Now, 1977, I was 27. This is where I saw this device. And I sort of realized, literally in a glance, that, I had two important moments in my life, technical life. See that, right? The first time I saw a laser in 1968, and I saw that little dot of light and went, that's impossible, right? And it's just like, oh, what's that? Of course, it didn't look like this. This laser, this helium neon laser was at least that big, and the power supply weighed a ton, right? And that's literally true. And then seeing this, and we're realizing, what was I thinking about? There's great things to be done. Then the Nova laser was built, another factor of 10. And then we decided we had to build an IF, which was another factor of 100. So this is step after step. So we started off with millijoules with Mayman, and then we went up to tens of kilojoules, and now we're going up to megajoules. So if you think about that, from megajoules to millijoules, right, we're going up 9 orders of magnitude. This is a lot faster than Moore's law. We laugh at Moore's law. Who are they? Okay, so then there was NIF groundbreaking. So since you guys are actually in a very political world, you think you're in a scientific world, but you're in a very political world if you're interested in energy, climate, and the like. And people are going to be looking towards you in the future for policy issues too, some of you anyway. And so we had to deal with politicians, groundbreaking. Then this does not look like your laser pointer. So we started to build this laser, and this is how it looked a couple years later. And this is how a laser bay infrastructure looks, in around 1990, 2001. That's a typical Livermore right there, up there. So you can see the scale, right? That's how it looks today. If you're ever up in the Bay Area, you have to let us know in advance. But you're invited to see it. We have public affairs tours, and it's much better in real life than it looks like in a picture. It's just, I've seen it a few thousand times and it still blows my mind. And this is how it looks from above. Now I want to show this is because every one of these beam lines, and remember our laser beams are 35 centimeters, or a little bit more than a foot square, not this little pixelated thing here, is the world's most energetic laser, every single one of them. And we have 192. And the reason, so that's why it's different. And it wasn't built to be the largest. It was built to be the energy that people thought it would take to ensure we would get fusion. So in some sense, it's not the biggest laser. It's the smallest, biggest laser that we thought we could get by with, right? So that's a little different view of it. So anyway, this is the target chamber. Where is that target? Okay. So remember that target. This is, that big. That's the target chamber. It's a lot bigger. That's a centimeter, and this is 10 meters in diameter. And remember, the target is a couple of millimeters. And the reason that is because of simple optics issues that we'll talk about. And also, you get a lot of energy out. And you talked about, megajoules of laser energy. And hopefully, someday we'll get over 100 megajoules of fusion energy out. And, you talk about, a bullet train or a 747, stuff like that. That's how much energy you're dealing with. And, and it's coming out not slowly, but in finally trillionths of a second. So that's why we had to make it a little bigger than you expect. This is how the building looked, and then this is how it is when we gently place that in place. And this is how it looks now. Now, what I love about this picture is this is 10 meters in scale, right? And you can see the laser, how the laser beams come in. It looks exactly like the target, right? Which is 2 millimeters. There's something in evolution that talks about that, scaling issues. So that's how it looks. And again, you can see, people here or here. Actually, I just want you to know it doesn't look this way. It's really 5 floors. So this was Photoshop at its best. So there's no view of NIF like this. Okay, so it works. It's very reliable. We're very happy with that. And then, of course, the politicians come back, right? Day one, they're there, and then, May 20, then when we dedicate it there. And there's the governor, who's actually a really funny guy, very technology-oriented and really smart. When you're with him, you're sort of stunned about, where he is in his head compared to where you might think he is in his head. And he also, he actually goes back and forth between the Terminator and kindergarten cop and the governor, like, so you go. He really understands the issues of energy and this stuff very, at least in my opinion, very well. Okay, so let's go back. Livermore, 1960. Okay, the 50 years just flashed by. So you can see San Francisco moved out on us. We used to be out in the country. Right now, you can see where NIF is. We told you how big it is. This is how it looks on the inside. It's a 2 megajoule laser, 500 terawatts. Okay, so 2 megajoules. Does anyone, we heard other views of 2 megajoules. I'll give you some different views of 2 megajoules. So how many, if you turn that into calories, how much would that be? How much food energy is that? It's a couple of donuts. That's disappointing. It's also a stick of dynamite, right? It's also, you know, a car going at 60 miles an hour. You got to think about this, as system people, which a lot of you are going to be. You really have to get yourself grounded in how you think about this. And the 500 terawatts is a different story. That's 1,000 times the power, peak power that the United States ever uses, right? So it's again a different story. Okay, so our goal is to get matter to incredibly high temperatures and high pressures and high density. So our goal is, get over 100 million degrees K, get over 100 billion atmospheres, and get over 100 times the density of lead, right? And do it really fast. You got to do it in billionths of a second. That's the goal. And that's a target. You guys saw a target. That's Bessanitas, the target engineer, lead target engineer. And this is how one looks like really carefully, not that simple one that you guys saw, right? And it's a highly developed physics device, right? This is not a production device. This is an R&D device. Remember, it looks big here, but it's that big, right? And so it's a precision engineering device. It has diagnostic capability all over it. You can stare at it in different ways with different, with X-rays, visible light, neutrons. It's kind of cool. And but when it gets in that target chamber, it sort of gets lost, right? Remember, that target chamber is 10 meters in diameter. We have to hit it within a half to a quarter of the diameter of your hair, and the target itself is a couple of millimeters in diameter. So big scale, little scale, long times, very short times, right? So we're doing nuclear physics, atomic physics, laser physics, right? All in billionths of a second. This is how it looks. So this is the control room. So it's okay. So this is how it looks. That's Glenn Hermes. He's shot this laser more than anyone. Okay, now we'll look at it, in animation. So that's electricity. Remember, you have to turn electricity to light to turn on the laser, right? And this is the master oscillator. We start off at a nanojoule, a billionth of a joule, and we're going up to megajoules. So the gain is 10 to the 15th. So first we go to a preamplifier that has it actually plays music, guys. So that is a 20 nanosecond pulse. So light travels a foot per nanosecond. Keep that in mind, okay? So that's 6 meters long. And every time you see that glass, it's going through neodymium glass, getting more and more energy. Now we're heading to the target. I'm going to cut down the noise a little bit. Whoop, that was... Okay, so that's the Lego block. Now we see some cousins coming in, 48 beams. Now we see another side of the family, 96 beams. This is a 10-story high building right now. All these beams have to get to the target at the exact same time, but they also have to be blue. Watch them time up. Now we see 192 beams. Now they're going to turn blue, ultraviolet, right? And now they go in. And you sort of get this picture already, right? This is now where the physics is. Now we're doing plasma physics, right? As we heat that sucker up. Now we're going to start doing classical physics as we build that rocket. Here's the rocket going. Now we're going to do hydrodynamics. Then we're going to do nuclear physics, right? So you're traveling through time and space. This is the twilight zone of physics, right? And it's happening very quickly. And if you can get that to happen, I'll be a happy guy, and hopefully, things will. And this is to give you scale. Remember, this is 2 millimeters, peppercorn. This is where it starts. We have actually done it to that scale. We've imploded targets that much, right? Factor of 20. Now that's good, but we have to go another factor of 2. Right, so that's where we started. We've gone down 20. We're really going for around 35. Now, that doesn't sound like a lot more, But for those of you who are hydrodynamicists, you know, when you have these growth factors and stuff like that, that's a big step. So that's what we're getting ready to do right now. And if we do that, we think it'll light up. So that's what we're going to be studying over the next year. So, you know, this is getting a lot of attention. You know, the cover of the Rolling Stones and fusion's great bright hope, and it's really in the news, right? And you're going to be hearing a lot more about it, I hope. Now, you might hear about another fusion too, which is called magnetic fusion energy, right? Which is a different way to do fusion. And so you're going to hear stuff in the very near future about this project called ITER, which is in Cadarache, France, which is having a lot of problems, right? Don't get confused. We are not ITER. We're not having problems. Right? You don't worry about the fusion on the sun, right? It's doing fine. The people will say ITER's not doing well. You won't go, oh, gravitational fusion doesn't work. Correct? You wouldn't say that about ICF either. Okay, so we've really made a lot of progress very rapidly, and we're getting ready to a place that we're getting ready to get doing actual burn physics. So remember, the goal is more energy out than in. That's how you know you have a propagating burn, right? Now, that doesn't mean you've broken the laws of physics, right? It's not perpetual motion, even though it looks like it, because you actually take some of the electricity you make in the future, not in the NIF, and take a little bit of that out to run the laser to keep the system running. But it's not perpetual motion, because remember, you've changed mass into energy. So as a physicist or as someone who's looking at conservation of energy, you have to look at that whole system, not just what's coming from the laser. So that's cool. I want to tell you another thing. In a T plus 1 minute, when deuterium and tritium and protium were made, when hydrogen was made, what we know as hydrogen and what we know as deuterium have sort of infinite life. But tritium has a short life, like 13 years. So it's sort of gone to first order. And it's being made in stars and stuff, but it's basically none on Earth. But what's cool about this, if we put lithium in the system, and I'll show you where, we make our own tritium too. So not only do we make our own electricity to run this, but we make our own fuel. That really sounds hard to believe. I'll show you how it works. I think another thing that's important, Secretary Chu, Steve Chu, who's from Stanford and Lawrence Berkeley Lab, he has been following the NIF, and he's gone through a journey with us. Because I got to tell you, there's a lot of people who've been skeptical about fusion for a long time, and for good reason. First of all, it's real hard. There's been a lot of promises for a long time. They haven't exactly been delivered, but here we are. So if you talk to Steve or Dr. Chu or Secretary Chu or Nobel Prize winner Chu, 10 years ago, he was pretty damn skeptical about the whole thing. And then over the time, he's come around a long way. In fact, he was here a few months ago, and he says we need to think about how to look to the future of fusion energy with a NIF-like system. Not NIF, right, which is an R&D facility, but with some derivative facility. And so the National Academy of Sciences and Engineering are about to study this. And this is kind of exciting for us. So let me talk to you about what this fusion power plant might look like. So we call it laser inertial fusion energy, or build a laser fusion engine, LIFE. And this is very conceptual, just so you can see it. It's not actually how it would look. But if you think about what's the problem with NIF, it fires about once every 10,000 seconds. So if you do that, say you got 200 megajoules out, or just say 100 megajoules out, and you do at a rep rate of 10 to the minus 4, right? So just do that. So 10 to the 8th joules, 10 to the minus 4, 10 kilowatts. You go. That's not a power plant, right? So you got to think about, if you want to get to gigawatts, you got to go up a lot in rep rate. And so what we think about is 10 hertz, right? So 10 to the minus 4 hertz, 10 hertz. So you got to go up 100,000 times faster. So people go, wow, that sounds like a lot. So I'm going to go back to Mayman. 10 to the minus 3 joules, 10 to the 6 joules. That's a factor of a billion. These are not insurmountable technology or engineering problems, and I'm going to show you we're already far along on our way. So our goal is now to think about how to do that. So this is how it would look conceptually. So this is a NIF target chamber, and here you're firing in the targets on a blowgun, right? Literally. And this is slow motion for the targets, right? And they come in, and they get hit by the laser, and they burn, and you get more energy out, and those neutrons come out, and so does some X-rays. So you get about 3 picojoules per fusion action, right? 3 times 10 to the minus 12 joules, right? And we collect that in this salt. And this salt is 60 centimeters or 2 feet thick. And this salt is really good because it stops neutrons. Neutrons are pesky because they tend to just go through stuff. They don't have charge, right? So they just keep going. But, there's some resonant absorptions in salts, and you can stop it. If there's a little lithium in there, you can make your own tritium, too. So we just collect it. And now we have this hot salt. And we run it by a heat exchanger, right? And we boil water, and we make steam and turn a turbine and make electricity. It's kind of pathetic in the end, right? Because the only thing a utility wants is a hot working fluid, right? That's what they want. Now, we really wouldn't use water. We'd use a supercritical CO2 or something. That's the idea. So that's good, though, because now when you look at the balance of plant, all those turbines and stuff, that's just normal stuff, right? You can buy that stuff. You don't have to invent all that stuff, right? But when you plug into that, in the wall there, the electricity you get will look like any other electricity you got, right? So you won't know that it's fusion until you go outside, right? Right, and you don't have any pollution. And when the global climate issue is sort of resolved, one way or another, which is another question that'll be resolved. If that, you'll be able to fight that, and you won't have geopolitics, and you'll have clean energy, and you got all of it you want. Remember, forever. This is how it really looks, though. It's a little faster. So that's 10 hertz. That's sort of a 10 hertz machine. So do any of you have any experience with 10 hertz machines? Yeah. Yeah, YAG lasers, or your car, right? Your car, 10 hertz is 600 RPM multiplied by 60. Therefore, anything that's an idling car is doing that. High-speed copiers are faster than that. Lasers are faster than that. So that's not an issue. But some people don't believe that. So here's a laser running at 50 hertz. Now this is sort of a different kind of laser than you're used to. This is a half-inch of steel. This is real time, right? And that hole is that big, 10 centimeters on a side. So, you can make lasers run at this rate, and you can make them high average power, which you would need. And you could make these. This is a green laser, as you can tell, not an infrared laser. And you can make them the colors you want. And so this is a future that we can do. Other people wonder about whether you can make those targets. Now, if you were doing sort of 5 times 10 to the 9th, let me go over this. Does everyone know this pi times 10 to the 7th seconds in a year, right? Everyone got that? You're going to keep that in your mind? Like a nanosecond is a light foot, right? And pi times 10 to the 7th seconds in a year, right? So if this is running at 10 hertz, it's pi times 10 to the 8th. So 300 million targets per gigawatt year of electricity. So if you multiply that by 12 or 13, you sort of get a lot of electricity in Northern California, right, or Southern California. So you need 5 billion targets a year. People say, could you do that, right? Well, just bullets, which are not a high production activity, are around 10 billion a year. What we're doing with them, I don't know, but there's a lot of them. Aluminum cans is 100 billion a year. I love Lego blocks. They're 2 billion a year. So when you look at this, if you look at the dimensional tolerances of this, what is the hardest dimensional tolerance? That's why you can use Lego blocks that your parents had, right? They just lock in, right? There's no wiggling. They'll last forever. And so And, you know, making these things at cost is really the issue. And so we're working with industry on that. Now, people, you know, we can think we're real smart. Again, I go back to this group, which has to look at all systems. What is the path to successful commercialization? It's not just science and technology. In fact, when you talk to people, you'll find out, even though in the science community there's a lot of skepticism, in the investment community and stuff like that, they sort of give you that you're smart enough to figure that stuff out. They don't ask you that question. They ask you, what are the economics? What's the time to market? What's market penetration? What's your supply chain? That's the questions they ask you. And so these are the things we've been really trying to consider, and maybe you should be thinking about too. And you know, when we look at this, the way the utilities look at life, they want to know what's the capital cost, dollars per kilowatt, right, for a plant, and what's the operating cost, dollars per megawatt hour, dollars per kilowatt hour. And then this is how much they charge you, right? This is what you pay on the, you know, what's coming out of your meter, because it's sort of the cost of capital, you know, whatever interest rate you have, you know, how much that cost, and the cost of operations, and then you get the cost of how much you use. They amortize that. And, you know, here's gas, and you can see gas flies up and down all over the place. That's because it's a commodity, right? This is why when the price, you know, when you go to the gas tank, you know, when you go to the oil tank, the gas station's going up and down. This is why people in the utilities and the process heat industry hate these things, you know, because their product is changing cost in a way they have no control over, right? If you look at coal, it's higher, it's capital cost, and it's not quite as volatile. But the whole idea that the United States will ever build coal again is pretty much gone, right? It's not happening, you know. Well, there's one plant being charged. If you look at nuclear, it's really not volatile, right? Because there's plenty of uranium. It's sort of been mined, and you don't really have to do anything. But the capital cost is just inching to the right. Sometimes it's screaming to the right. And that's a problem. So when we look at life, it's kind of an interesting place because the fuel is well known, and the capital cost we think is simple to predict. It looks like it's very competitive. There's two different types of plants that we're talking about. But I got to tell you, I'm skeptical of this chart, right? We haven't gotten ignition, and we haven't built this stuff, but we already told you how much it costs. But, you know, as a systems person, when you're thinking about future energy technologies and how they were going to play out, you really have to keep this in mind too. Because if this were way over here, you know, or if it were way over here where solar or things like that are, you know they're going to be stuck in boutique type industries, subsidized boutique industries, until, you know, someone finds a way to crack through and bring them into this playing field. And the reason I say that, if someone said that, you know, you weren't paying $70 a barrel for gas for oil, they said it was going to cost $700 a barrel, right? A factor of 10, just won't happen, right? So when you think about these things, you know, that you have to think about that, and that's why we think about life. We're really working on these issues. So where are we going next? Can we get life into this, you know, initial challenge? Now, the answer is we think we have a story for getting ignition, and I'm going to show you I think we have a story for getting commercialization. And here it is. Here's our roadmap. 2010-ish ignition, you know, 2020, a prototype plant, and we're talking to a lot of people about this. 2030, that's a long time, it sounds like, 20 years to commercialize. It's really kind of, if you go back to my original graph, right? You know, it would, you know, 20 years is considered fast. And by the way, you couldn't get it into the marketplace any faster if you wanted it to. And then 2050, if you could have a major part of the world's fleet of energy production, fusion, you know, you would be on your way to changing the, you know, economic carbon model for our civilization. And that's what our goal is. Now, how does that play, just to go back to the United States? Here's a model that we looked at to reach 25% life in 2050 and 70% by 2100. By the way, that model is based on replacement of infrastructure that exists now and is being built over the next 40 years, right? You can't just get in, right? No matter how good an idea you are, it's really hard to displace everything. And what we find, if we could start building in 2030, and by 2040 be building one a month, by 2050, we would be 25%. So you can imagine taking out 25% of carbon and replacing it just with fuel from water. Not only that, this is semiconductor technology, it's high tech, the technology itself is clean and useful. And this will then go on from there to whatever the world decides it needs. In fact, what you'll decide, because by 2050, as I said, you will be the world leaders who will be making the decisions about how this goes. So, life, it's laser inertial fusion energy. It's based on NIF, it's based on R&D that started 50 years ago, that's coming to fruition now. It's sustainable, it's carbon-free, it's passively safe. It doesn't seem to be a proliferant technology, which is really important. It's highly modular and compact. It's separable. That means different people can work with different parts of it simultaneously, which is really important. And we think that it could be piloted in 10 years. So we're not alone on this. So I just want to end with this. We are clearly the world's leaders, but the Japanese, the Chinese, the Russians, the Brits, the French and the European Union are following us. And that's a good thing, because that sort of affirms that you're probably on the right trail. But, it also makes competition difficult. But, competition brings out the best. So we're up to this job, and we want to have this happen. So we believe this could be a part of our energy future, your energy future. If you ever want to see the NIF, come by and give us a call, a couple of days to a week in advance, and we can probably arrange it. And if you, in the future when you're looking for jobs, think of us. Okay, thank you very much.
So we'll do about 5 minutes of questions here. And first of all, I want to say thank you. It was a great talk, and for all you people out there, do pay attention to it, because Livermore does keep hiring. And believe me, when they come down here, they want to talk to students. We think it's a great place to work. So, give that little advertisement. Questions?
You talked about having an implosion right now of factor 20, and you need to get to 35.
That's radial and distant.
Radial compression distance or implosion distance, and it sounds like you're expecting to get there by the end of the year.
Okay, so I said in the next year we'll be doing experiments to do that. The reason right now we got 20, which was sort of what we expected, is we're using gas-filled targets, which is just deuterium helium targets. They're not frozen targets, and they sort of bounce. They go, and then they just bounce off. What we're doing now is putting solid layers in, which have a very much lower entropy. So you launch them on a low adiabat, so they should coast in, about a factor of 2 further. The real issue isn't whether they'll coast in. No, that's not unlikely. The real issue is, as they coast in, will they stay nice and round, spherical as they go in? If you have any defects in it, people always talk about put an egg yolk in your hand, right, and squeeze it, right, really fast and try to compress it. Well, what will happen is, as you know, it'll just squirt out all over the place. Those are really Taylor instabilities. So that's what we're working against. So can you get it to keep going in smoothly?
And you mentioned in your last slide that there are 5 to 6 other international efforts. Are they all basically using the same technology, the neodymium glass, and the same target configurations, or is there some significant difference in their approach?
If you look at this, the first order, they're, except for Z, which is an pulse power type way, they're all using neodymium. They're using essentially the same targets. We're using indirect drive. That's that can. Where is that can? Is it still going around? Okay, you got it? Okay. So that's indirect drive. You turn the dry photons into X-ray photons. There's another way to do it. You can just get rid of the can. It's called direct drive and just hit the light right onto the capsule. When you go through it on, the naive view on paper is it's a better idea, but when you really get into it, those Rayleigh-Taylor instabilities get out of hand a lot easier. So the first order, everyone's following the same approach.
So is there something shaped to make the X-rays focus towards that ball? I would think they'd sort of be isotropic method.
Well, no, actually, you work really hard to make them isotropic, and it's not that efficient. The goal is to have as close to a spherical drive as possible. And so what you do, there's no board here, but anyway, what you do is if you look at the little oven, you have 3 rings of light. And if you unwrap that, you have 3, lines of light. And it's sort of like in not this classroom, but in normal, fluorescent lights, right? You have 3 things. So if you're going along on the floor, it looks very, very smooth. But you're right. That means it's not quite as efficient as you want. And that's that whole thing of going to direct drive, which looks more efficient. So the goal is you throw away efficiency to get smooth drive. So that's the answer.
Yeah, so I'm a chemical engineer in my background, and it seems to me that
You know the old joke about chemical engineers? Someone at the lab I know was asked whether he was a chemist or a chemical engineer, and he said, "Who gets paid more?" He said, "Chemical engineers." He said, "I'm a chemical engineer." All remember that.
So it doesn't seem like the fusion is the difficult part. It sounds like, you're not doing cold fusion, you're just doing a really small amount of, what they did in the bomb, right, the atomic bomb. So the question in my mind is not how do you do that, but how do you harness that? And you showed them the nice illustration with the molten salt, but I have a lot of questions about how you actually catch all that energy in a molten salt and then transfer it to another fluid, that heat into another fluid. And what happens if it cools down for a minute and it's no longer a molten salt? And I think that's where the real question is at.
Well, I hope you're right. But to be honest, okay. So the answer to the question is, well, what kind of salt would it be? It's got to be a salt that's good at absorbing neutrons, right? So you get them all to first order. And there's a lot of salts. And does it have good thermal properties? That's really important. And other questions are, is tritium soluble in it? You don't want the tritium to dissolve in it. You want the tritium to be not dissolve in it. And do you want it to be non-corrosive, because it's going to be a hot flowing salt, which can be very corrosive. And I think you're right. That's a challenging question. Fortunately, people have been working on this. There's all kinds of salts called Flibes, Flynac, and other stuff that sort of meet the bill. So this is an issue. The question is, well, what if it froze up? God, that would be an ugly day. And the answer is, when you go through the thermal capacity of these salts, they're really large. And the issue is quite the opposite of freezing up. Just keeping them, from, if you lost a pump or something, from really getting very hot. So those are important questions. There's decades of work on it, and there's a lot of people working on it in the nuclear industry and all the fusion industries. So those are very good questions. But there's a lot of things that you have to consider, right?
Okay, we'll take 2 more.
Yeah, and a little practical question about the line flow side, because right here you're shooting in 10 centimeters a second, but they're made out of gold, say 1 gram or so. I was just wondering, why don't you just paint the whole chain there in gold, basically, because you're introducing a lot of gold, and fuel will burn up, but you still have the residue, the gold residue.
Okay, so this is a really good question also. It's actually a better question than you're stating. So you got these things. Say we're a gram. It's much less than that, but it doesn't matter. And say you were doing, we'll say it's a few milligrams, which is a better view of it. So, but say it was 100 milligrams, and you did 10 a second, so that's a gram. And, in 1,000 seconds, you have a kilogram, and blah, blah, blah. All of a sudden, you got a lot of crap floating around, right? What if it were gold? Well, first of all, that would cost a lot of money, right? And second of all, gold, when it condenses, will not, has a melting point that's very high. So it'll just stick wherever it is. And over a while, you'll get stalactites, stalagmites. It'll just sort of be a messy situation. So you wouldn't use gold. That's, for physics experiments, gold has a higher opacity, less leaky to X-rays than other materials. But there's other high Z materials like lead, which are almost as good. You only lose a couple of % in opacity, has a lower melting point. When it flies around, you'll still be doing that. And now it'll generally, you won't have a Teflon, first of all, but it'll generally just keep flowing. It's also, and over time, it'll drain out the bottom. There are still issues, detailed issues of thermal management, so there are places where, you condense out these materials. So those are engineering issues of great interest. It's a good question, but not gold.
We'll take one more here, and just come up here and ask questions.
The width of the laser beam was about a foot.
Say it again, please.
The width of the laser beam, the 190 about a foot. And then, by the time they hit the target, what is the spot size? And
Okay, so this is a good question. So why would we want them a foot here, right? And then have them, about a millimeter on the target, right? Okay, so the answer is real simple. If you need them sort of you need them to have a big enough area so that you can have enough ions that you deal with so that you can get enough energy, right? If you had them really small and you had too many ions, you can't get that high density ions in the glass, so that wouldn't work. There's another issue though. Now you have to make them big because the energy density on the glass gets so high that it'll start damaging the glass. So we work really hard on that and have pretty much solved that problem. But now that you've done that, so you now have a laser that has enough ions to get the amount of energy and you have enough area not to burn up the glass, now you have to get onto the target. So now you head for the target and you really would like to have the target pretty small, right? But now we have the next question. When we start heating up this target, we make a lot of plasma, right? And what does the plasma do? Every time you look in the mirror in the morning, a metal, you have these free electrons and you see your pretty face, right? So now you instantly make a plasma in the target. It's a nonlinear plasma. So now your steering beam's changing colors, reflecting them. That's why we make it blue. And then we do one other thing. We try to make the lights, after working so hard to make this beautiful coherent light, we make it incoherent. we put some bandwidth on it, so we make it FM, and then we put it through a very special kind of dephasing optic. So it's very smooth when it gets to the system, no coherent blotches. And we put that all together, and you sort of have all those trade-offs going all the time when you're doing it, and that's the answer. So it's about a millimeter when you get on the target.
Okay, great, thank you. Let's thank our speaker.